Hi, everybody. Welcome back to the second lesson in the Prep for Precal Semester 1 course for the summer. Again, we're covering a lot of material today because I think you'll notice when you get into the course this fall, they go through 3 chapters of material really fast because it's all review. So if I've reviewed you for the review, it should make how fast those chapters move that they have to cover in order to get to the new material. It should make it a little easier for you. That's the goal. So today I'm covering everything that's in chapter 2 of the Precal book, which again is all review from either Algebra 1 or Geometry or Algebra 2. So today we're kind of focusing on more function stuff, but particularly different types of functions, not just functions in general. So the first thing we've got to be able to do is identify what a type of function is from a graph. So that's pretty easy. You've learned 9 function families. Linear, which you know what that looks like. It's a straight line. Quadratic, which is a parabola. The inverse of a quadratic, which is a square root, looks like this. Absolute value, which is our V-shaped graph, right? Exponential, which is a curve that flattens horizontally, and logarithmic, which is a curve that flattens vertically with that asymptote. Cubic has this wiggle in it going left and right and up and down, but it looks a little more vertical. Cube root is same thing, goes up, goes down, goes left, goes right, but it has a little bit more of a horizontal orientation. And then rational is that one type of split graph that we've had where it has asymptotes in 2 or more places. So I need you to be able to identify those. You can tell hopefully that this is a cube root, whereas this is the V shape. This would be absolute value. So no real math there, just identifying by a picture what type of function you're looking at. Now, really want to hammer home, and you're going to see this in a couple of different lessons this year, this semester, this summer. Let me rephrase that. Connecting roots and x-intercepts to graphs and factors, maybe even tables. Remember that a root is known as a solution, an x-intercept, or a zero. Those are all synonyms meaning the same thing. So if you have a graph, can you look at where you see it crossing the x-axis and identify the solutions? Or even be able to write a version of an equation that could match that graph. Also, keeping in mind that you're looking at graphs that have a certain degree, like this is a quartic function because it turns 3 times, and it has, I know it's an even-powered polynomial because it's in behavior. This is going down. This is also going down. That means it has to be an even polynomial. The highest power needs to be an even number, whereas this one goes down in one direction, goes up in the other. That end behavior is different, so that must be an odd-powered, odd-degreed polynomial. So keeping in mind the degree of the polynomial tells you how many roots there are, even if some of them aren't real and visible on the graph. So I know this is a quartic function, 4th degree polynomial. So that means it should have 4 roots. Now, they may not all be real. So let's look at that. Remember, everywhere something crosses the x-axis is a real solution. Now, I only see 3 solutions here, 3 different roots. However, there is a bounce happening here. And remember that a bounce, when it doesn't cross the x-axis, but it bounces at it, that is a repeat root or a repeat zero. So that accounts for 2 of the 4 roots, plus this one, plus this one. There's our total number of solutions. So this value right here, which I believe is -4, happens twice. Remember, that's called multiplicity. We don't need to write it twice, but it definitely accounts for 2 of the 4 roots. It crosses through 0 and it crosses through 5. And so these would be my real solutions. Now, can I take the idea of real solutions and be able to write an actual factored form of that polynomial? Now, this is a cubic, right? This is a 3rd degree. So it should have 3 roots. Do I see it crossing in 3 places? No, I actually only see it crossing in 2 places. But again, I see a bounce happening here. And so I know that that is going to account for 2 roots, and that means 2 of the same factor. So if I see that the real roots appear to be at 2 and at 6, but I see that the 2 happens twice. Remember, as factors, even though this is a positive 2 and a positive 6, I'm going to be writing those factors with a minus. And I'm going to make sure I have 2 of the ones at 2 since there was a bounce there. So I want to pick which one of these answers has 2 roots at 2 and 1 root at 6, and it would have to be this one. And you could have written this one as x minus 2 close the parentheses squared. They just didn't choose to do that. Remember, if you ever just see an x, that means that there's a root at 0. And that is not the case here. So we did not want to choose that one. Okay, this set of notes has 8 pages. It's not going to take that long. It just looks long because of all these pictures. There's a lot of graphs in this one, so it takes up a lot of room on each page. So let's practice that again. Here, we see that there's only 1 root that I can see. But I know this is a cubic, so what that means is it should have 3 roots, but I only see 1. I only see it crossing the x-axis at 5. What that means is I must have some imaginary roots. So if I look at, I can definitely go ahead and say that if there's a root at 5, the factor would look like this. So this does not have that choice. This does not have that choice. Now, if we look at the 2 remaining, what's left after the x minus 5 should give us 2 imaginary roots. I have 1 real, I have 2 imaginary because it turns before the x-axis. So that's the sign that there is an imaginary root. Actually, there's always going to be an even number of imaginary roots since we use the conjugate, the opposites. So I definitely want to pick something that would give me, if I solve this factor for x, I would get a negative square root, and that's going to happen here. So I'm going to choose this one. If I were to set this one equal to 0 and solve, I would get 1 and negative 1, and I should visibly see it crossing at those 2 places on this graph, and I do not. So I'm not going to pick that one. This would give me the imaginary roots that I'm looking for. This gives me a real at positive 5. Okay, let's look at this next one, practicing that same thing. Now here, again, it's a cubic, 3rd degree, so it has 3 roots. I visibly see 2 places where it crosses the x-axis, but again, I see a bounce here, so that one gets to count for 2 of the 3 roots. It'll just be a repeat. So I see real at negative 2, I'm sorry, that's negative 3. And at negative 1, and this one is multiplicity of 2. So I need 2 factors that say x plus 3, since that's a negative 3 root, and one of them that says plus 1. So I look at these and I see there's only one that has all pluses, and it's this one. And that would be true because these are all negative valued roots. So the factors should be positive. Okay, now let's look at increasing and decreasing intervals. That's something that we definitely talked about a lot at the beginning of Algebra 2, and then we kind of brought it up off and on throughout the year. It's going to pop its head up right away in Precal. So remember, when looking at a graph, it's easy to spot where a graph is increasing, always reading a graph from left to right, and where it's decreasing, also from left to right. You may be asked to write the intervals of increasing and decreasing, and you use x values, and you do either inequality notation or interval notation, and they give you those options down here. You never include any beginning or ending numbers in your intervals. Never include those in your intervals, meaning don't use the equal to line in your inequality notation, don't use a bracket in your interval notation. So if we look at this graph, we see that from here to here, it's increasing, and from here to here, it's decreasing. This question is just asking for the increasing interval. So from this point where the x value is 0, to this point right here where the x value is 4. So from 0 to 4, this is an increasing interval. So you could either write that like this, that's inequality notation, or you could write interval notation. So here's inequality notation, here's interval notation. You pick one, but don't use brackets, don't use equal to lines. But this has a distinct beginning and end, so I don't need to use any infinity symbols, and it is just one particular increasing interval. So you may also be given a question where it asks you to label all of them. And remember, if there's ever an interval that is not increasing or decreasing, those are constant intervals, and you won't use them if you're just being asked to find these. So if you had something that was going completely straight across, that's a constant interval. Don't use that in any answers where they're asking for increasing or decreasing. So if we look at this, I see that there's 3 pieces to this graph that's called F, and 2 of them are increasing, 1 of them is decreasing. So the first thing I'm going to do is select, it talks about segment 1 and segment 2 first. So segment 1 is first, and that is definitely an increasing. There will be a drop-down menu, and that's from the x value of -6 to the x value of -2, reading from left to right. Then segment 2, and they talk about that next, that is a decreasing interval, and it starts at the -2 where the other one finished and goes to an x value of 4. And then starting at 4 all the way until 8, we have another increasing interval that goes from 4 to 8. And so here they're practicing inequality notation. All right, now let's switch our brains away from increasing, decreasing. Another thing that we looked at as a behavior of a graph is when is it positive, when is it negative? And that refers to what intervals are above the x-axis and what intervals are below the x-axis. And remember, on the x-axis is not either positive or negative. That's a neutral location. So we won't use equal to lines here or brackets unless it doesn't have an arrow and it clearly stops at some value that is either below or above the x-axis. Okay, so if we look at this, it says, name all of the values of x for which the function is less than 0. So here they're asking for negative intervals, and there may be more than one. So if I look at this, I see from here to here, which is 2, it is below the x-axis, not including 2. And it's also below the x-axis from 6 to infinity. And these should both be, this is negative infinity because this is going forever to the left. So forever to the left, all the way up to 2, I have a negative interval. And then I have another negative interval from 6 to infinity because it keeps going to the right from that value. So I would be writing something that showed, if it asks for interval notation, it would look like this, from negative infinity to 2, this piece, and also from 6 to infinity, this piece. I'm only going to leave out the x values between 2 and 6 because those are not satisfying that condition. All right. So if they're just asking for negative, these would be my 2 intervals on this particular graph. Okay, another characteristic of a polynomial graph or some of our functions is the difference between a relative or local, also known as a local extrema, maximum or minimum is what that means. Extrema just means terms or ending points. And then absolute, which means in the whole graph. And not all functions have absolute maximums or minimums. A quadratic does. A quartic does. Any of our even powered functions will. Our absolute value does. But if it's not one of those, it's going to have local maximums and minimums, also known as relative maximums or minimums. So a vertex, like an absolute value vertex or a quadratic, that is definitely an absolute extrema, either a maximum or a minimum. Any turning point in a graph that isn't one of those is called a local or relative. So A couple of things we're going to do. First of all, do we remember how to use our technology to find a minimum or a maximum where we expect it to not be an integer? So I want to remind you guys that we have the TI Inspire that will allow you to find any minimum or maximum coordinates. If they ask you for the minimum or the maximum, they're just interested in the y coordinate, like the actual height of that graph at that particular x value. So I'm going to move over to a graphing calculator here, and you can use Delta Math, you could use Desmos. In fact, let's just use Desmos because I prefer Desmos, the graphing calculator. And I'm going to type in this function that they've given us in our notes. So 1.5x squared, squared, plus 7x plus 1.8. And if we look at that, we can see that the coordinates of the vertex, and it wants us to round to the nearest hundredth, so make sure you read carefully, would be negative 2.33, comma, negative 6.37. So we want to make sure that we write that correctly. So, but when they're asking me for the minimum, I'm actually just interested in how low does it go. It goes to negative 6.37. And that's us using technology to help us find that. There we go, to find that minimum. So I've listed it here. Now, if they ask you for how many maximums or minimums there are, pay attention to whether they're asking for absolute or relative / local. If we look at this graph, this is a cubic. It doesn't have an absolute maximum or minimum. It goes down forever, it goes up forever. But it does have a turning point here, and it also has a turning point here. This is called a relative or local maximum. Not the maximum of the whole thing, but of this portion of the graph, it is the highest point. And then we also have a local or relative minimum down here. It is a turning point where it is at its lowest going back up. So it has a total of two relative, it's only asking for a maximum, so I can only put one. It does have, let's just go ahead and write that. It does have a relative minimum as well. Minima is just plural for minimum. It doesn't need to be plural because there's only one this time. Okay, A, C, and E, those are distractors. Those are x-intercepts or roots, but they're not part of the answer to any maximums or minimums. All right, so let's look at our next one, end behavior. We talked a lot about end behavior with all our different functions in Algebra 2. So remember, when you look at a picture of a graph and you look off to the left side of the image, like as you see the picture that's been graphed and you look off to the left, you can observe the end behavior as that graph's x values travel towards negative infinity. As we go to the left, x values are always going towards negative infinity. Conversely, as we look at the right side of the graph, it's traveling off the right side of the coordinate plane. You can tell the end behavior of that function as its x values are going further to the right towards infinity. So I'm looking here and I'm looking here. Remember, functions with even degrees, like quadratics, quartics that have a fourth power, they're always going to have the same end behavior in both directions. So I can obviously tell that this is not an even degreed polynomial. Functions with odd degrees are going to have opposite end behavior. So, and that's what's happening here. This one's going up, this one's going down. So I know this is probably a third power or cubic function. If the polynomial's leading term is positive, it will be pointed, it will always increase to the right. That's not what's happening here, so this must be a negative. If a polynomial's leading term is negative, the end behavior will always decrease to the right. You can literally just look at the right side as the x values are increasing towards infinity to determine the degree of a polynomial, or at least know whether it's odd or even. So if we look at this, the first of all of these say as x is going towards infinity, so this is where x is going towards infinity. What's happening to the y values? They're going down. So I need to pick something that shows this phrase. Okay, I don't like that. That would say as it's going to the right, it's going up. That's not what's happening here. Now, as x approaches negative infinity, which is this part of the graph, it's going towards the left. What's happening to those y values? Well, they're going up, so they're going towards infinity. I definitely want that, or that. I don't want this or this. So the only answer choice that is left that doesn't have a slash through it would be that second one. As x goes to the right, the graph's going down. As x goes to the left, the graph's going up. That's exactly what's happening here. All right, then we talk about average rate of change. An average rate of change isn't necessarily the rate of change. First of all, we never use rate of change except for linear. Average rate of change can be used for things that are not linear. Portions or intervals of a graph, you can give an average rate of change even if the graph itself is not linear. You have to be given an interval to be comparing. So you're going to have a problem or a set of problems in your assignment where it's asking you to compare like a graph to a table to an equation. And all of these are three distinctly separate functions. That's why they have different names. This is f of x, g of x, and h of x. They give you an interval that they want you to go investigate between -1 and 4, including both of those values. What is the rate of change of this graph, of this table, and of this equation? And you're going to put them in order from least to greatest, like most negative rate of change to most, well, if they're all negative, you'll just put them in order the way they would fall in the number line. So for example, this graph right here, if we look at the x value of, if I look at the x value of -1, the function is sitting on the x-axis at that point. So it has a y value of 0. If I look at the x value of 4 on this graph, the y value is, notice that these are counting by 1s on the x-axis and 10s on the y-axis. So it is -20. When x is 4, y is -20. So what's the rate of change here? Well, these differ by losing 20, and these differ by gaining 5. You could always do the slope formula on these, like this minus this over this minus this. That's what you would get, and that rate of change is -4. Now, if we look at this particular one, g of x, here's our starting part of our interval, and here's the ending part of our interval. So how different are the y's? And how different are the x's? So I went from 13 to 18, that's a difference of 5, and I went from -1 to 4, that's a difference of 5. So this has an average rate of change of +1 between those 2 points. And then this function right here, -x squared minus 3x plus 12, plus 13, you can either algebraically plug in a -1 and a 4 and use the slope formula to find its rate of change. You could type this in and go to a table and look for those points of -1 and 4 starting x values. I'm just going to go ahead and plug this in. So h with a -1 put in, h with a 4 put in. So here I would get 1 with a negative in front of it, plus 3 plus 13, that would be 15. And then here I'm going to get -16 minus 12 plus 13. So that would be -15. So h of x has a difference of, it loses 30. Well, yeah, it loses 30 when it gains 5. The x's changed by 5 every time. That was the number on bottom of the slope formula. It was just the y's that were different. And so yeah, between -1 and 4, it lost 30 in the y's, but it gained 5 in the x's. And so that has a rate of change of -6. So now that we have our 3 average rate of changes and we compare from least to greatest, this would be, out of these 3 numbers, that is the smallest. So h of x should be listed first. So I don't want to choose any of these. Then the next smallest was f of x. And then the biggest rate of change was g of x. So this is what I want to choose. So it looks like a lot of work, but it's really just kind of a slope formula, and a slope formula, using the same 2 x values to represent that interval. Okay, so now, this is pretty easy. What if you know that we just practiced putting in x values into a function and getting the corresponding output. X's are inputs and y's are outputs most of the time, right? So you can evaluate a function for any input. Like if you are using f of x and they tell you to plug in a 6 for x, you can get the output that goes with that. But you can also be given an output and have to work backwards and find an input. Sometimes it'll be linear, sometimes it'll be quadratic, sometimes it'll be an equation, sometimes it'll be a graph. We have to be able to respond. So this is a function that they give me, and they tell me to put 7 in place, not of x, but of h of x. Basically, the y value is being replaced, and we're just solving for x. And you can do this easily algebraically, and we would get -3. That would be the corresponding input for an output of 7. If you're given a graph, it says this is f of x. Find all the values of x when the function equals 2. So that means when the y value is equal to, what is the x value? Well, I actually see 2 points on this quadratic that have a y coordinate of 2. The x value of -1 does, and also the x value of +1 does. So you'll want to hit -1, the comma to open up a second box, and then +1. Remember, you can always hit a comma to open another answer box if you have multiple solutions. Okay, let's also review domain and range. And remember that we've learned about in Algebra 2 inequality notation you knew about from Algebra 1, and then we introduced these 2 other ways of writing notation, set notation, notation of domain and range. Most of the time we use interval, right? Every once in a while they'll throw a set one at us, and we can do that too. Remember, domain is from left to right of a function. Range is from low to high. Once we got more complex functions introduced in Algebra 2, domain and range sometimes was a little trickier. For example, square roots. We have limits. This has to stay, what's inside the radical has to stay real, so it has to not ever fall below 0. So what do we do when we have a square root function and they're asking us for the domain? Well, we need to set this equal to, or actually an inequality that keeps it above or equal to 0. So you can take that inside of the square root, what's inside, and put that in inequality and solve for x. Keeping in mind that when we have an inequality, and at any point, if we divide by a negative, we have to remember to flip the inequality. So what this says is I can keep this inside positive as long as I'm sticking with x values that are -3 or less. Okay, so that's your domain restriction. So you could write the domain that way. You also could write it as -∞ to -3 with a bracket around the -3. Yeah, you also could write it in set notation like this. X stays less than or equal to -3. Those all mean the same thing. I think you're free to use any of those options. If not, go with the one that it's kind of pointing you towards. Now, a rational, they have at least one x value in the denominator, which means there's at least one value that's not allowed in the domain, where there's either a whole or a vertical asymptote. So if you're given a rational that is anything other than linear on bottom, probably going to have to factor it. Factors of 7 that add up to 8 would be 1 and 7. Yeah, there we go. I need to set anything in the denominator equal to 0 to figure out what x is not allowed to equal. This would be -1 and this would be -7. So it's basically saying I can use any numbers in the domain. Any value of x can go into this and it will have a corresponding part on the graph, except at -1 and at -7. So in set notation, that could look like this. X cannot equal -1 or -7. It means everything else is fair game. You could write interval notation to say anything from -∞ to -7, not including -7, and anything from -7 to -1 will work, but not including either, and anything larger than -1 will also work. Those both say the same thing. This is longer, this one's a little shorter, but we're not as comfortable with set notation, so you kind of have options there. But basically, you can always put it in here and just show it's the set of all real numbers of x, except x cannot equal -1 or -7. All right, function operations. We talked about this at the end of Algebra 2 when we did some operations, adding, subtracting, multiplying, and dividing functions. That's what we're doing today. So we're just combining the like terms, the things that we can, with addition and subtraction, and then multiplying using our multiplying polynomials strategies and then dividing, we typically divide by factoring. That was the easiest way to do those. So this one says we have f of x and g of x, and we are multiplying them together. So you have options. You know how to multiply polynomials together. You can use FOIL, which is really just extended distribution. Or you can use a box, totally up to you. I'm going to just use FOIL. So x squared times x squared times 7, 10x times x, 10x times 7, 21 times x, and 21 times 7. And then combine my like terms. So I have x to the third, I have 17x squared, I have 91x, and I have 147. That's my answer. I multiplied. Here's f of x and g of x. Now they're asking us to subtract. So I'm putting the one that was listed first, minus, and put parentheses if it's anything other than a monomial. If it's a monomial, you don't need the parentheses, but if it has more than one term, you do, to make sure that minus sign gets distributed to everything that is in that second function behind the minus sign. So that's going to change the sign of x and the sign of -3. And if I combine these, I end up with this combined answer. And then we've got division. So put what's listed in the denominator on top, or what's listed at the beginning of the division problem, and what's after the division sign needs to go on bottom. I think the way we did it was we factored factors of 40 that add up to -13. And if there is any common factor on top and bottom, cancel them out. What's left is the answer to your division problem. It's not even a fraction anymore. And then I think the last thing that we need to talk about, there's a couple more things, but piecewise functions is a big one. Piecewise functions we introduced in Algebra 2 because it does show up right away in Precal. So piecewise functions are random pieces of different functions put together in the same graph. Sometimes they're touching and they're perfectly connected. Sometimes they aren't touching and there's gaps in that graph. Here's a picture of a graph that they want us to take this linear function, and so we're going to choose linear. We're going to see that this has a slope of 1. So you're going to hit this button, and it's going to bring up a linear graph, and you are going to move it if needed to where it needs to go. Now, this is the parent linear function. So when you press the linear button, this is a negative sloped linear, this is a positive. So we actually want to pick this one. It should give you the linear parent function, which is this. And then it's going to ask you to click done. And then you're going to, there's a line that's going to pop up that basically is like a cropping feature. We're going to crop it so that we're only seeing the x values that are -4 and further to the left, or the less than. The x values that are smaller than -1 are found. So you'll press this button. You won't even need to shift it up, down, left, or right. You'll just take the crop line that they're going to give you and shift it over to -4, and make sure you include -4. So we want to make sure that there is a, that right here, that there's a solid dot, and you're only going to want to show things to the left of that dot. Now this one is a quadratic, so when you press this button, it's going to put the parent quadratic up. This is 2 up from the parent. This is the parent quadratic, but shifted up 2. So you're going to bring it here. It's going to give you the whole parabola, but then you're going to take the crop line that you get once you have put that and shifted it up 2. Then there's a next step where the crop line is going to pop up, and you're going to move it over to negative. It's going to come from this side actually, and you're going to move it over to -2 because that's the x value where this interval is starting, and keep everything to the right of that value. So you'll end up with this point here, and you're going to be taking everything. You'll be using all of this, but none of what was up here, because that's all where x is less than -2 and you only want greater than. This is what your answer should look like if you do it correctly. Now, if they just give you equations, and here's 3, this is a piecewise that has a linear, a constant, and another constant. you need to make sure that you recognize and can understand that this is saying between the x values of -4 and 0, you'll use this. For exactly 0, you'll use this. And for anything larger than 0, but only up to 3, you'll use this. This is asking for an x value of 0. So when x is exactly 0, the function's value is 6. And that's all I'm going to put there. I didn't even have to substitute into an equation. It was a constant, so I know the answer is 6. And then could we do the opposite? Like, could we look at a graph that's already graphed and find a specific function value? Remember, when you evaluate it, you've been given an x value. Look for the x value at -1. It is possible, if you have a graph with any gaps or open dots, that there is no value for the function at that particular x, and you would click the button that says undefined, and that is a choice down here. Now here, if I go to the x value of -1, if I look up, I can't include that as I can't say 3 because that's an open dot. I also can't say -9 because that's an open dot, but right here, I have an included point at -1, the x value of -1. So I'm going to write that the function's value is -4 at the x value of -1. This does include the x value of -1. And then also, you do have some problems. I'm not doing any examples because it's really that easy. Do you remember how to tell if something is a function? If you have a group of ordered pairs, you're looking for no repeat x's. If you see a table, you're looking for no repeat x's. If you see a map, you're looking for, mapping looks like this. Make sure that there's only one arrow coming out of each x. So if there's 2 arrows coming out of a certain x value, that would not be a function. So I just want to make sure you remember that. On a graph, you draw a vertical line. The vertical line test will test if there are any repeat values, x values in a graph. All right, the last thing we're going to talk about are transformations. Remember, we have worked with so many different functions, and we did include b in some of these, but we can use that with a linear. We can use that with a quadratic. We could use that with an absolute value. We can use it with a cubic. We can use it with a square root. I mean, all of these had the same general behaviors. H moves something left or right. It's the opposite of what it looks like. K moves things up or down. A's will stretch or compress something if we change it from a 1 to something that's not a 1. Remember, the sign will flip it. If the A sign flips, it's a reflection across the x-axis. If there's something inside a square root or inside absolute value or inside something being squared or cubed or any of that, if that sign changes in front of x, that's going to be a reflection over the y-axis. And then if A gets bigger, ignoring the sign of A, but the absolute value of A, if it gets larger, that's going to be a stretch vertically. If it gets smaller, ignoring the negative sign, if there is one, it will be a vertical shrink or compression. If B gets larger, we have to flip it over and then determine if that's a horizontal stretch or compression. So I've written all that up here. So we have a couple of things that will practice that for you guys. If you look at this, the parent, this is a square root graph. The parent is graphed for you. That's what we see here. This is the parent. If we put a -5 inside the square root with x, that is an h change. And so that means that h is moving the graph right 5. And it's the opposite sign. So when I see a minus, I want to think left, but because it's inside the square root with x, I'm actually moving it right. So you're going to take this and you will have the option to shift it. And that's it. That's the only change that happened here, was that it was shifted. Okay, so you'll just shift the whole thing to the right 5. Here's a cube root picture. This is the parent cube root. That's what is graphed for you here. Now, if I take it and I vertically, This is an A value in front of the cube root. It is not a 1. It is something bigger than a 1. So that's a vertical stretch. Then what I would do is I would keep this here. Nothing was shifted left, right, up, or down. So keep the inflection point where it is. Notice that vertically to get to the next point, I go up 1. So what I wanted to do is go 3 times bigger than that. So I'm actually going to take this and go up. I'm not adding 3. I'm multiplying this vertical distance of these 2 points that were originally 1. I'm multiplying it by 3, which means this is going to go up times 3. This one is 2 away from the inflection point, so I need to go up 2 times 3 to 6. And this one this will also be a distance 3 times greater, and so will this. And so this is where my points should end up. This is a cube root function with a vertical stretch of 3, and that's what you should be seeing when you move those. And then the last thing is any function that we're given. If we see an original, which is the black function, the dark one, we want to convert it to the dotted one. And I love this because it's an actual animation. So as you make changes, it will show you what it would look like with those changes so that you can change your mind if you want. But if you look at this is a downward facing quartic, but they want it to be an upward facing quartic. So I must need to change this sign to the opposite sign from what the default. The default will always be positive, positive, 0, and 0 for A, B, H, and K. So I definitely want to flip it upside down. When I do that, it would look like this, or it's a little lower, sorry, like that. That's good because that looks like it's the direction of this particular one, but then I also need to shift it. I need to shift it right, and I need to shift it, I think, slightly up. And so play around with the numbers. You can always look at a point, like this point is going to become this point when I flip it upside down. So when I flip it up, it'll still be on the x-axis, but it'll look like it'll be right here. And so I would say, okay, I need to move that 5 to the right and 4 down. So to me, that would look like 5 to the right and 4 down. I would be putting those numbers in there and changing this sign to flip it upside down. And that's it. That's just every problem is something like what I just showed you on the notes. And I hope you guys have a nice week. And we'll see if I can stop this recording.